All right, we're looking at our last lesson here in our polynomial function unit on the applications. So our goal is that we can apply a polynomial function to a word problem and state an appropriate domain for the context of the problem. All right, our first example, or our only example with multiple parts here that we're talking about, is the forces acting on a horizontal support beam in a house cause it to sag by d centimeters, x meters from one end of the beam. The relationship between d and x can be represented by this polynomial function. Now, if I expand and simplify this, you should be able to see that that would be a degree 4 as the highest exponent on the x, so it's going to be a quartic. It is a positive lead coefficient, although it's very close to 0. It's 1 divided by 1850. But it should have my end behaviors going to positive infinity on both ends of it. Now, degree 4s could have at most 4 x-intercepts, and it could have as few as 0 x-intercepts. That is something we should also add to our summary sheets. First part here says determine d at 7 and explain what this means in the context of the question. So we're replacing the x with 7, and if we look at what x is defined as, it's x meters from the end of the beam. So if you have your beam in your house, ideally it's totally horizontal, but as forces get applied, it might sag a little bit. I grew up in a very old farmhouse, and the floors were definitely not level because over time the house foundation settled, and it was over 100 years old when I was living there, so wasn't in the most sturdiest of shape, shall we say. All right, so this 7 is 7 meters from one end of the beam. So if this is the end of my beam, I'm just looking at what the D is, 7 meters from the end of the beam. How much is it sagging by? How many centimeters does it sag from horizontal? That's really what this is calculating. All right, so all you need to do is replace the x with the 7 and see what that calculates to be. So we're going to have our 1850 here. It's going to end up timesing the x or multiplying the x. And then you still have your 1000 minus 2 times 7 squared, and then plus 7 cubed. And you calculate that all out and get an answer there. And I believe when I did that, as long as I didn't make an error, which is entirely possible that I did, I got a 1.37 out of that. Okay, so 7 meters from the end of the beam, there is a slight sag there. It's 1.37 centimeters or 1.4 centimeters. All right, so I should write a therefore statement with that. All right, so I typed my statement there explaining what this calculation means in the context of the problem. All right, try part B, evaluate D at 15, and again, explain what it means in the context of the question. Part C, you're just going to graph the function using graphing technology and sketch the graph in the space provided. Okay, when I calculated D at 15, I got a negative 1.01. So if there truly is a sag to the floor, instead of that horizontal, we are dipping down, but what this is saying is we have a sag of negative, so instead of being this, we're actually bubbling up, okay, bubbling up our floor possibly, but it's quite unlikely that if it's a solid beam that you're going to end up having it move upwards, because gravity works and it pulls things down. So my guess with this answer, it's not really making sense. My thoughts are, if I'm 15 meters down the way, maybe this 15 meters isn't part of the domain. It's maybe the beam is shorter than 15 meters. Okay, so that's what this is calculating the sag at 15 meters from the end of the beam, but my mathy senses are telling me this doesn't really make sense. Okay, so hopefully that's also making sense with your brain in terms of how you need to know a little bit about how things are constructed, but usually your beam is placed on vertical supports so that you have your ends and then it'll sag between those two vertical supports. It shouldn't bow or move upwards from there, but then again it depends on your horizontal compression if there's something happening that way. Anyway, Let's move on and graph the function. We'll see what it looks like, and it's using graphing technology, so get your Desmos going here. I'm going to slide over to the next slide to do my little sketch of it. But get your Desmos out, because then you can actually tap on important pieces, important points. Okay, so I have my graph sketched here, very shakily sketched, but it is sketched. I've located where the zeros are, and I've only listed the x coordinates for them. So this was at negative 6.18, 0, 10, and then 16.18 is what I got for those values. Now, what is the domain and range of the original function, not considering context of the question? So your domain, because we keep going over to negative infinity for x and over to positive infinity for x, your domain is just all real numbers. So without context, it's just x such that x is an element of the reals. Now, because this is both ends are going to positive infinity, we need to search out where the low values are. So if you tap these points here, these are local minimums. All right, if you tap on Desmos and check out the y coordinates, they end up being both the same, and I got y coordinates here of negative 1.351, and the x coordinate where that happened was a 13.66 on this side. The x coordinate's not really important here. What we want is the low y coordinate, and the other value was over here at negative 3.66, comma, negative 1.351. So our y values are at negative 1.351 and bigger than that. So our range will equal y such that our y has to be greater than or equal to negative 1.351, comma, y is an element of the reals. Now, the range I would not necessarily ask unless you had a graph with the point labeled on for you. As I said, the little max and mins that are in the middle of our function with polynomials, that's a calculus thing that we get to further after advanced functions. All right, what's the length of the beam, and explain how you know. Now, assuming the beam can only sag and not buckle, I'm looking at these spots here, and x, which is this axis here, the x represents the distance from one end. So if we are at the end of our beam, x would go positive from there. And I believe if we can only have sag, and this is tracking in positive values how much it's sagging, which is opposite to actually drawing a sagging beam, but it's just tracking how many centimeters it's sagging by. Back here, by the time you get to 10, there's no sag again. So I'm thinking the length of my beam is that 10 meters based on that context, based on the fact that we have no sag at 0, we can't have negative values of x because we wouldn't be on the beam at all, and then we're moving forward to 10 where it has no sag at the 10, and then after that is where we get into the opposite sign, and we would end up with buckling happening. But again, assuming the beam can only sag, we're looking at a 10-meter beam there. All right, so that's how we know that. Okay, as far as domain goes then, our domain starts at 0 and goes up to 10 based on the length of the beam. So our domain would equal x such that 0 is less than or equal to 10, x is less than or equal to 10, and x is an element of the real numbers, because you can have parts of a unit for lengths or distances. Now, in terms of range, again, because I have my Desmos in my graph, if I'm only looking at that part that we outlined here, for my x values, my lowest y coordinate in that section would be 0, my highest would be here, and when I put that in Desmos and tapped on it, I got a point of 5, comma, 1.689, or almost 1.7. 1.689 is that spot right there. So our range will be between 0 and 1.7-ish. Okay, so we could write that in here. That's our y, or in fact this context of the question was our d at x, so we could put d at x instead of y, which I'm going to do if I can find my, there it is, my eraser. We've got d at x, because that really is my y in this case, such that 0 is less than or equal to my d at x, and I'm just going to put less than 1.7. Okay, it's 1.689, so we'll just go less than 1.7. Y d at x is an element of the real numbers. Okay, so we're restricting the domain and range for the context of this problem. All right, so your job now is to work through some questions on the back side of this handout. And some of the questions tell you explicitly to use technology to help you with them. Otherwise, you should be trying to solve the problem without using technology. All right, good luck.